Hi, everyone. I apologize that I cannot be there with you. Today, I will talk about separating human text from AI generated text, and I'll focus particularly on the detection problem involving two classes. One class is text that is generated by a language model, and another text that is generated by language models, but then undergone some edits by a human. Okay, so the motivation for the problem comes from the many AI detection tools that perhaps out there, and perhaps some people think it's important to detect text that is generated by AI. Now, the problem with those approaches is that they do not address what I call is the typical use case of text of AI to. So think that you want to write an article and you want to be assisted by an AI language model. So you may do you will go to ChatGPT, you ask ChatGPT to write an article here about get a text. And perhaps you want to for more specific things like here is the issue with the airports, and perhaps comparing the airports to competing gadgets. In this situation, we will take all those received from ChatGPT and we can perhaps create an article. Comparison be in Samsung Galaxy Buds could be a subsection of this article. So altogether, what I'll get is what I call an AI generated text. Okay, an article generated by ChatGPT. There is a human in the loop here, but it was generated by GPT. Now, I received this article. This is I still may want to make some what I call human edit, perhaps the moving sentences, and eventually what I'll end up is what I call is an AI generated text with that was edited by a human with human touch. Questions that we can ask in this situation is first, whether can we detect those human touch, whether we can say was the text was edited or not, and also whether we can tell where those edits might be. Okay, so these are the challenges that we'll address. And what I'll do is I'll present you a method, see how it works, how well it performs, and then try to convince you that this method is really motivated from very robust principles. So first, the method. Before the method, a word about terminology. We have here in this talk two kinds of language models. One is what I call a predictive language model or a classical language model. This is simply gives me the next token probability. Okay, this is what usually we refer to as language model in the literature. Okay, so GPT falls under this category, and all Shannon's N-gram models are here. And on the other hand, we have the generative language model, which is named what I call a machine that generates tokens. Okay, so for example, ChatGPT is falling under this category, or any language model with a sampling mechanism falls under this category. Okay, so engineering-wise, these two may be very similar, but for the context of this talk, I want to separate the two. Okay, so we have a predictive language model and a generative language model. Okay, what's the method? How does the method work? The input, you have a text document broken into sentences, and we have three steps. First step, we do what we call a per sentence testing or sentence by sentence testing. It means for each document, I will evaluate the log perplexity of the document, okay, with respect to the language model of my choosing. And then I will use this log perplexity to test the individual hypothesis that the sentence was written by the generative language model. Okay, I summarize the evidence using a p-value. And I'll explain in the next slide what is log perplexity. The second step is global testing. And here we use higher criticism to do the global testing. So we combine all the p-values using the higher criticism statistic. Here, p, the brackets denotes the order statistic of the p-values. Okay, so this all together, we get a test against the global null, stating that all sentences were written by the generative language model, okay, perhaps with some other assumptions like independence. And at the end, what I'm doing is I can use higher criticism also to try to identify where those edits might have been. This is done using the higher criticism threshold that was studied by Dono and G. Okay, so what about the log perplexity test? So log perplexity of a sentence with respect to a predictive language model is the sum of log probabilities that the model gives to the text. Okay, so this is what we also call log loss. Okay, this is what usually the language models that we work with are trained to minimize. So this is the test that we will apply. Okay, so you see that this test seems to have some power when we check it on test data. Okay, so here the blue curve is the curve generated by text generated by ChatGPT. The red curve is a human text that is of similar topics, and you see the receiver operating characteristic that is have some non-trivial discrimination power. Okay, so let me show you really the results or some results. So first, we'll work with synthetic data. Okay, so it's always challenging to get results, especially in this case where the data has multiple layers of creating it. So let's start for sanity check with a control environment in which we create the article by planting sentences from a non-AI source. So we can find a data set or several data sets in which there's a specific topic and there's a related human text and there's a related text that is generated by a language model. And what we can do is replace epsilon fraction of those text generated by AI with human ones, human sentences, I mean. Okay, so here is an example. This is a data set that tries in which we ask GPT-3 to write Wikipedia style articles. Okay, GPT 3.5 or something, Wikipedia style articles, and we also provide the first sentence of the article. So you see this sentence is identical to the true sentence in Wikipedia, and the rest is not. Okay, so here is the topic is British chess, and what we'll do is we'll mix. Okay, so we will take the AI article and we'll replace randomly sentences with sentences from the human article, and overall the topic will be relatively coherent because both discuss the same situation, the same topic. Okay, so here is how it looks like. Okay, so as you can read. If you could read, the red parts is written by human, the black part is written by GPT, and you think that this seems to be quite a text that seems to be coherent. Okay, so we have data sets like that, we have different sources, and we can apply a method to this text when we can also control the mixing probability or replacement probability, and also you can control somehow the number of sentences per article that we have, and you'll see that over here is the power of the method when we fix the level at 0.05, and you see that this result seems to be quite nice, quite indicated the method has some definitely non-trivial capability of separating things with especially for larger replacement probability and also for longer text. Okay, so the situation is affected by the replacement probability and by length of the text. Longer text is better, higher replacement probability is better, more signal in both cases, and this is not surprising. Okay, so here we use the GPT-XL as the log perplexity detector, even though the text itself is GPT 3.5. All right, we also tried this using synthetic data, but this time, in a more realistic scenario. What I did is we took several topics. When we ask ChatGPT to create articles, those are usually were taken from Wikipedia. We asked ChatGPT to create the articles, and we prompted it also several times with subsections from Wikipedia to fill out, to write based on those, until we reach to some number of sentences which is satisfactory for us. For example, like above 50, between 50 to 200, and then we took a human editor, several human editors. We asked them, hey, please edit this text for us. Try to use as much as possible by the addition, replacement, or removing sentences, and overall try to improve the text until you reach to an edit rate of about between 10 to about 20%, although there are some cases in which they did not reach this edit rate. And then we apply the method, and we can see how things work. We can translate the higher criticism value that we obtain into a p-value, so low p-value meaning good detection or successful detection at the significant level of our choosing. So, and you see that that seems to be working in the sense that it's in most cases it gives us good discrimination. Okay, so that's was the empirical part and the description of the method, and now I want to explain to you why what we're doing here makes sense. And for that, I'll bring up some. I'll study each part of the steps in the method from an information theoretic point of view. Okay, the first, the log perplexity detection. Here we will work with what we call a probability low p, and a probability low p in that generates a probability low p over a sequence of tokens. And this is what in information theory called an information source. In NLP, we'll call it a language model. When we sample from this probability law or from the information source, or in other words, in which the information source generates tokens, we mean that they generate a token according to the law that the ith token is the probability is generated from the model conditioned on the previous tokens. And perhaps there is some initial state here or initial context, T naught. And now we introduce to the situation on the second probability law, okay, G. Here, G will be stand for generative. And what we assume here is that PG is a stationary ergodic information source. Okay, it's a bivariate information source. And if we sample now tokens from the model G, then the log perplexity of the sentence under the model P converges to the cross entropy rate of the model P under the model G. Okay, so in words, if we sequentially sample tokens from G, the average log perplexity under P converges to the cross entropy rate of P with respect to G. Okay, so the cross entropy rate is the population log perplexity in our situation. The interesting thing about the log perplexity, the cross entropy rate, is that it is we can decompose it using the entropy rate here of the model G, which is non-negative, plus the Kullback-Leibler divergence between G and P, which is also non-negative. So altogether, this whole situation is minimized when P equals G, and otherwise we're getting something that is larger than the entropy rate of G. Okay, all this bring us to the conclusion that first, the limiting value of the log perplexity is minimal under the true token generating model G, which means that we would like, as much as possible, to work with a language model P that is as close as possible to the token generating model in the Kullback-Leibler divergence sense. Okay, so this is also indicated on the specific limitation of the method. For example, we usually cannot evaluate the log perplexity with respect to the generative language model, so we have to satisfy with some P that is maybe this not may have a non-zero DKL, okay, significant DKL. We also have this result was asymptotic. So in real cases, we might encounter sentences which are very short, so we don't expect the convergence to be very dominant there. And in other words, in those cases where the sentences are very short, we expect that the initial states, or sometimes called the context, could affect things. And this may want us to think about ways to improve our detector by incorporating context. Okay, this is at the end of the talk, the last slide. All right, the other aspect of the method is step 2, is using higher criticism to combine the evidence from the perplexity detector. And here it makes sense to use higher criticism if we think about a relatively naive sentence generating model in which we sample from the generative language model in most cases, except in rare situation where we make an edit. In this case, we will sample from the human model. Now, this situation also incorporates a mixture model for the p-values, and we know that higher criticism is especially useful for this kind of sparse, rare models. Particularly, it is information theoretically optimal in the sense that it detects the achieve the signal rarity, sparsity, rarity, signal strength phase transition. Yeah, so a higher criticism, hopefully, and its usefulness in this situation is clear in this form. We have hundreds of papers discussing the theory and applications of this tool. So now let me summarize. Hopefully I could convince you that detecting edits in text generated by a language model is a challenging task, but it's still possible to achieve. And we did it using a method that is based on a procedure that is can be motivated very well from information theory, okay, under a mixture model for sentence editing. This model also tells us what's affecting our accuracy and also how. Okay, number of edits, length of text, and also the closeness between the predictive model and the generative model in the KL divergence sets. So this also brings us to some open challenges that exist based on what you see here, and I'll be happy to discuss all those challenges offline because I'm running out of time. So thank you for listening.